All right, week 2/12 and lab 9. So a quick thing I wanted to say is these videos are here to help you and I want them to be helpful. So I had a lot of people give me some great feedback, a lot of that in terms of what do you want to see in this video. A lot of people told me I don't want anything to do with the lab, I want this to all be practice problems, Victoria, I need help on the exam. And I said, that's fine, I hear you. I will definitely try and make that more tuned to that. So a lot of this is literally me talking about the lab for 2 seconds and then letting our lovely head TAs talk about the actual lab, and then me going through actual practice problems and past exam problems that have to do with this lab / with this whole section of the chapter. So if that's what you want, then cool, that's what this is going to be from now on. If that's not what you want or you want something else, let me know. We might do 2 videos, one where it's a bit more lab-based in general, and then another where it's a bit more exam-based in general. We'll see how that goes, but I do need to hear back from you. And I also noticed not a lot of you are watching these, and sadly the ones who are watching this right now are the ones who are happy to be here and are doing that anyway. So please tell other people in the class to watch these, because sadly on the lab reports I definitely saw who did not watch this video and also who did not watch the videos posted on Blackboard in general, and it was very evident in the lab reports. So please share that with your fellow classmates, please. And also, if you're watching this just before the exam, welcome. Hopefully you're not cramming. Hopefully this is something that you're not doing last minute and you're doing this well in advance. But if you are not, skip ahead really quick, go through the problems, basically see the problem, work through the problem, and then check your answer against my work. If you get the same answer but work through it differently, make sure that the way that you worked through it is not just a trick, and that this would not work for every problem. Ensure that the overall method is correct, aka don't use M1V1 equals M2V2 for your Ka concentration sort of mapping of acids. Don't do that. So make sure again that the overall method is correct so it can be applicable to everything else. But other than that, welcome, and we're gonna get on with the stuff. So quickly though, I wanted to show off that I have been having a wonderful time at home. I've been making this puzzle. It's been so good. I finished it yesterday and I was so excited, so I thought I'd share it with you all. So I wanted to quickly show you my puzzle before we moved into this. All right, weak monoprotic acids versus polyprotic acids. So you can read this for yourself. I'm also going to post this help page later on today, maybe on Friday, I think your quiz is due on Thursday, so I'll post it Thursday morning, Wednesday evening. Because I don't want this to confuse you, because it is just a block of information. That's why I'm posting the main block that you need for your quiz here, and then I'll post the actual giant document that has like a lot more information than what you need on your help pages part of Blackboard. So for now, this is just the part that you need for the lab and for the pre-lab and all of those things. So I wanted to compare these because a lot of people have been asking me what monoprotic versus diprotic / polyprotic is. Literally, protic is proton, so monoprotic means it has 1 proton, diprotic means 2 protons, polyprotic many protons, etc. And the reason why that matters is that the more protons you have, the more dissociation constants you have, because basically as an acid breaks down, it loses hydrogens, and this means that every time we lose a hydrogen, we are dissociating, and that dissociation is relevant to the acid itself, and in some cases a base. Can be polyhydroxyl bases, but we don't mess with that. That's too much for me and too much for all of us. So this is going to be here for you to look at. Please look at it, pause the video, whatever you got to do. And then I'm going to post the full document on Wednesday evening. So you can have it for the quiz on Thursday, but I wanted to highlight for those who do watch these videos the important bit here. Okay, so quick lab 9 overview. Things that happened last lab that I can't have happen this lab is the M1V1 is not used for titration calculations. It is used for the dilution calculations, and that is it. And the reason for that being is that this is telling you that there's a direct molar concentration dependence between the two things, and we are never ever saying that with the titration. We only have it happen sometimes in this way due to equal amounts of volume or similar molarities, and it gets you somewhat of the same answer. But if you do not have that, which is why it only works for very specific cases with strong acids and strong bases, because they have a 1-to-1 mole ratio. But It does not work all the time. You must show the molar ratio dependency because, again, it's a dimensional analysis. I commented on those who did miss this, but I would go back and double check the percent calculations. Not all of them were correct. I think all the people who wrote down the actual equation for a percent mass calculation got it correct. So I would say maybe do that first so it kind of refocuses you on what you need to plug in. Email me if you don't know what that is. And then please don't give up. There are so many people who had blank answers because they didn't know how to find pKa and then of course didn't know how to find the Ka value. Please email me. I don't want you guys to leave things blank. It shouldn't be left blank. You guys can definitely send me an answer. And these are things that I'm happy to help you with. And also it was in the Piazza page, which is why I don't want to say I took no mercy, but I definitely took off marks. And I was a bit generous this time. I will not be generous this next lab report because it's on Piazza and I'm saying it here. Please just email me if you have questions about this lab report in anything, especially procedure, because it's hard to find a procedure through online. So a little bit of coffee here. All right, lactic acid. So I'm going to quickly pop into the questions. Lactic acid is a waste product that accumulates in the muscle tissue during exertion, leading to pain and feeling of fatigue. This is something you feel. And in part A, we already noticed that we're using 0.1 of an aqueous solution and it's 3.7 dissociation. So we can set that equal to the concentration of H plus over the lactic acid, and then we work through and we'll find that the Ka is equal to the concentration of the H plus times the concentration of the conjugate acid all over the total concentration of the conjugate acid, which we can see we get all from above. Cool. Now, something that I wanted to highlight here really quickly is that H plus and the conjugate acid are going to equal each other. I literally just did the ice table in my head because for Kas, the idea is that you have an X change, but we know that we have 0.1 to start off with initially already of our lactic acid, so then I know that H plus and the conjugate base are going to be 0 and therefore X. And I also know that my Ka is so small that I don't have to take the subtraction of X. So moving on to part B, I can already see the pH of 3.56, so I can already find the concentration of H plus. I plug that all into my ice table and I get my Ka value. Notice that this did not follow the 5% rule in the denominator. And because it did not follow the 5% rule in the denominator, this means that then I do have to take into account that X value subtraction from 0.1. So here I wanted to show the whole ice table and the 5% rule because this one does not follow. And then as well, using the same calculation from part A, I can then work backwards and do the same thing to find the percent for my ionization in this one. So this just works a bit differently. So, before I move on, take myself back to the start. So basically, I went through this very quickly, but pause the video, look through the work, and then follow my work and see if that made sense. So 0.1, 3.7 dissociation, 3.7 divided by 100, that is 3.7%. I rearrange it to get this this equation, and then thus finding the concentration of H plus. All right, not going to review that again, but again, pause and make sure you understood that, and we'll move on. So a student titrated 20 mils of a sample of solution containing a weak diprotic acid with a strong base, and that strong base had such and such mils in concentration. Okay, cool. So I'm going to calculate the concentration of the weak acid first before moving on to this molar mass stuff. So I look at this problem and I already can find the equation of the chemical equation, and then I know that I have 20 mils of an unknown concentration of my diprotic acid. And I know that because I can see here in the equation, let me get my pen, that I am calculating the concentration. So I already know I don't know it. Cool, so I'm not looking for it. And then I do know the concentration of my strong base and its volume. So I'm going to quickly plug that in. Again, no, I have done the molar ratio. This isn't M1V1, and I found the moles of my diprotic acid. Awesome. And notice I'm only taking into account my reactants. We're not going to take into account water. It doesn't count. And then our conjugate base is not important yet. And not important in this because I'm looking for the concentration of my weak acid. So I find the concentration by doing moles over liters. Again, the moles of the diprotic acid is 0.02 because of 20 mils. Now, Molar mass is grams per mole. I do know the grams. That comes from my equation, 0.5025, so I plug that in, plus I know the moles. I get the moles because I already found the moles when I was trying to calculate the concentration, so I'm just gonna plug that in down here, type it into my calculator, and I get 402. Awesome, just what I wanted. All right, again, pause that video, make sure you understood what's going on, make sure you understood why I was doing it this way. Again, the best way to work through these, pause, look at the question, work back, and be like, do I know how to do this? Can I do this now? Can I make this chemical equation? Can I find that 20 mils is equivalent to an unknown concentration of my diprotic acid, etc.? All right, so predicting whether an aqueous solution of the following salts are acidic, basic, or neutral. So this is section 18.7 of your book, and I put up 5 new ones. So this is similar to something that you might have seen on your recitation sheet, but we basically look at this by the strong acid, weak base formalization. So I look here and I got potassium perchlorate. You and I know that potassium perchlorate, when I think of its conjugate acid to the perchlorate anion, which is ClO4-, well, I know that hydrogen perchlorate or perchloric acid is a very strong acid, and therefore the perchlorate anion is a very is a base, and therefore, and it's a weaker base, but in this case would then make the overall salt basic. Same thing to do with my sodium prononic anion. The prononic anion that matches with the sodium is going to come from is going to be basic, because the sodium comes from is our spectator ion, and so then I know that when I look at the acid, the conjugate acid of this is weak, and therefore it has a very strong base, and the strong base would then equivalent to making a basic salt. All right, now I look at chromium nitrate. Nitrate comes from a strong acid. Strong acids make weak conjugate bases. That weak conjugate base is then going to mean that the overall thing is neutral. So if I have weak conjugate bases or weak acid salts, weak conjugate acid salts in the salt, it's then going to be neutral. So the same thing here with the cesium bromium. The bromic acid is a very strong acid, and therefore its conjugate is a weak conjugate base, and therefore the overall salt is going to be neutral. And then finally, I look at my methyl ammonium chloride, and I know that the methyl ammonium is actually coming from a weak conjugate, and therefore it's a strong conjugate acid. So its base is actually very weak, and therefore, because it has a weak base and turns into a strong conjugate acid, I then know that the salt is acidic. This is a tough concept to grasp, and it takes a lot of things to memorize, but I would say mostly memorize the acids and strong bases as we did before we went on break. So be sure to email me if that doesn't make sense, but this is the overall idea, is remembering that strong, weak association. Okay, scene 8. What is the sulfur concentration in a saturate solution? So I'm going to quickly pull up my pen here. So this is already a diprotic thing because it says -2, and I can tell this is going to be tough because it's pH adjusted, and that always freaks us out. So I also can see that it's diprotic because I've got 2 Ka values. So this means I'm going to be losing 2 hydrogens at the same time. So I got S2- and I'm losing 2 hydrogens. Wonderful. Okay, so I set up my dissociation equations. There's going to be 2 of them because I have to show that each time I lose that hydrogen plus. So I've shown that here. Again, 2- kind of gives us that hint. And then I plug in my Ka1 and Ka2 values. I know that I'm going to add together these 2 equations to get me an overall equation, and then that means I'm multiplying my Ka values. So I bring this all down, and I get my Ka equation to equal Ka1 times Ka2, which is 1.1 times 10 to the -2. Cool. My Ka then equation is going to equal this. Again, we got products over reactants, good to see. Don't forget that 2 squared. And then I rearrange this to find my concentration of S2 minus. So I'm gonna then plug, emphasis. Again, that's what we're looking for, S2 minus concentration, and I plug in my numbers. Now, where did I get these numbers from? I know that I have a 0.1 molar concentration of H2S, and then it's pH adjusted by 6. So I get 10 to the minus 6, and that's literally from my equation that I write, and I'm gonna try and write this. pH, there we go, pen's working. pH equals the negative log of the concentration of hydrogen. So then I'm working backwards. If I do 10 to the negative 6, that is going to be my concentration of my hydrogen ions, which of course is what we're looking for in this, because that's our only missing variable. So I plug that all in and I get my concentration of S. Oh, wait, no, take me in. Oh, take me back in. Oh, keep going. All right. Nope, there we go. Final question. So when I have a 0.1 molar solutions of these solutes, I need to arrange them in increasing H plus order. So notice that they're all the same concentration. I'm going to pull up a pen. That's going to be really bright, I can already tell. So this is the correct order. Now why is this? First, I know KOH is going to be the least acidic because we got a lot of OH going on. Large OH concentration is always low. Now my KCN here is going to be next because that CN is coming from a weak acid salt. And a weak acid salt is then going to mean that it's a strong base, and so it's basic, if that makes sense. Yeah, so and thus it's a strong base and therefore basic because it's a weak acid for a salt, and therefore we go that way. Next, I'm going to look at my ammonium bromide. In my ammonium bromide, I'm going to note that this also comes from a strong acid, and therefore it's the salt of it's the conjugate base, and therefore a weak how to say this? Comes from a strong acid, and therefore this is a weak conjugate base. I'm changing the color. This is too bright for me. Well, and therefore it's the salt of a strong acid and a weak base, and therefore it's acidic. And then H perchlorate is a strong acid. Sorry, I had to change the pen. That was getting too bright for me. My eyes were hurting. So again, come back, and replay. There we go. Just gonna redo this. But yeah, basically when you look at them, be sure that you are looking at these as their conjugates. So first of all though, I already know this has a lot of OH minus in it, so that's already going to mean that it's very basic. The next one is that KCN is the weak acid, and therefore it's weakly acidic, comes from a weak acid, and therefore is going to be a strong conjugate base. But it's not OH minus, so that means OH minus is always the strongest. Then I'm going to move to ammonium bromide. Ammonium bromide. And ammonium bromide is the idea that bromide comes from a strong, bromide comes from a weak acid, and therefore is is the salt of a strong acid, and therefore it's a weak base. And because it's a weak base, the overall concentration will be very acidic. So HBr, as you remember, is a weak acid, and therefore the salt is a strong acid, and that would mean that then the Br, it's overall going to be weakly basic, and therefore it's acidic, and then my hydrogen perchlorate is a strong acid. Cool. So my overall comments to you is please email me, especially about the concepts of weak acids, strong bases, conjugates, etc. It's very confusing. It's not something that you just, I think, understand. It takes, first of all, reading it through, understanding what you don't know about it, and then, making sure you understand the concepts, especially when it comes to weak acids and conjugate bases, and then how their salts are then influenced by the weak acid or coming from a weak acid or a strong acid / a weak base or a strong base, and how that relates. So you'll find that sometimes you get it and then you'll go back through it and you'll convince yourself of something else. So just make sure that when you read it through and you make up your mind about what it means, stick to it and make sure you keep that through. Please email me about that concept. It is a tricky concept. It's something I remember being very confused about and having to work through a lot. So please let me know what you think. Other than that, I hope you guys have fun with your lab and also with your homework. Please email me, of course. And if you're reviewing this for the exam, good luck. I'm sure you're going to be fine. Move on to the next video, though. You got no time because I'm sure you're cramming. So